In this video, I'm going to show you a proof of theorem 4.4, which is slightly different than the one in the book. I'm going to use the bridges that we talked about earlier. So how do we prove that every tree of order n has exactly n minus 1 edges? Well, let's see. So we just established that tree means every edge is a bridge in a connected graph, right? That's what we did in the last video. So let's use induction on n, somewhat similar to the proof in the book. So n equals 1, meaning just one vertex. The statement is true because a tree on one vertex is just a tree with no edges, and that is n minus 1, so that's okay. And so now let's do the induction step. So we assume it's true for all values less than n, and we want to show it for a value n. And how do we do this? Well, we have a tree, so n is at least 2. So in particular, there exists an edge e in my graph. So now here's my graph with an edge e. Now I know it's a tree, so this edge is a bridge. So if I take it out, I'm left with two components. And these two components have some number of vertices. Say the left component has k vertices, the right component has l vertices, and I know that k plus l is equal to n, because that's the total number of vertices in my graph. So these components, these are connected graphs, they're components, without cycles, because they come from a tree. And so by deleting an edge, we're definitely not creating a cycle. So each of these are trees. So this means that this left component has k minus 1 edges, and this right component has l minus 1 edges. So in total, we're getting k minus 1 plus l minus 1 plus the one edge e in our graph. And this is k plus l is n, so this is exactly n minus 1. And this is the whole proof. So we don't have to first establish that we have vertices of degree 1 to work with. Of course, this theorem that every tree has at least 2 vertices of degree 1 is very handy and is useful in many proofs on trees. And in fact, we can go on here. Let's move this and look at this theorem too. Theorem 4.3, every tree has at least 2 vertices of degree 1. And let's prove this from what we just know, the other way around. So how do we know this? Well, so every tree on n greater or equal than 2 vertices, we need that. So tree means n minus 1 edges, because we just established that, right? So this is our proof here. N minus 1 edges means the degree sum in our tree is 2n minus 2. But this thing in a connected graph is always greater or equal than 1. So if all but one vertex had degree 2, or bigger, then the sum here is greater or equal than 2 plus 2 plus 2 plus and so on plus 1, which equals 2n minus 1. But that's not true. That's a contradiction. So we have to have at least 2 vertices of degree 1. So this is another way of proving that we have at least 2 vertices of degree 1 in a tree, which again is a useful statement to prove many, many results about trees.